So this lecture is going to talk about the central limit theorem. So let me start the show. Okay, so the central limit theorem, we can call it the CLT for short. It's a very powerful thing that we use in statistics. So there's two different forms of the theorem, and both alternatives are concerned with drawing finite samples of n from a population with a known mean and a known standard deviation. So again, we're talking about populations. We know the mean and we know the standard deviation. So for this lecture, we're going to concentrate on one part of it, and then the next lecture we'll concentrate on the next part. So the first alternative says, if we collect samples of size n with large enough n's, we can calculate each sample's means and create a histogram of those means that result the histogram tending to have an approximate normal bell shape. All right, well, what the heck does that mean? What that means is this. It means I can take a ton of different samples, and within each of those individual samples, I'm going to find each of their means. So say I have like 100 different samples, that means I'm going to have 100 different sample means. And those sample means are what I'm going to plot on a histogram. And when I do that, it's going to make a bell-shaped curve. 100 samples might not give me a really nice bell-shaped curve, but if I keep going to 1,000 samples, 1,000,000 samples, anything over that, I'm going to have that beautiful bell-shaped curve, and that's what that means. Now, the second alternative says if we collect enough samples of a certain size that are large enough, we can calculate the sum of each sample, and it'll make a histogram too. So what does that mean? Again, we're taking samples, and each of those samples, within each of those samples, I'm adding the numbers together to get the sum. And if I plot those sums, I'm going to have a nice histogram with a normal bell-shaped curve. And again, I'm talking tons of samples. I'm talking thousands, millions to make that bell-shaped curve. But this approximation means that we can take unknown samples distribution, say like it's exponential, it's skewed to the left or the right, and if I keep adding more samples, eventually it's going to make that bell-shaped curve. So when we talk about it too, we're going to talk about the size of the sample n is supposed to be large enough. So for us, we're going to say the samples need to either be over 30 or over, and it needs to, or the sample has to have that pretty bell-shaped curve. And as we keep going on, as we move through inferential statistics, you'll see that a lot. Is my sample size 30 and above, or is the data normally distributed? So if the population is far from normal, we need more observations for either the sample means or the sample sums. Okay, the sampling is done with replacement. So it'd be difficult to overstate the importance of this, but it is such a powerful tool, and we use this all the time in statistics. So let's talk about the one where we talked about the mean. All right, so if you remember back in normal distribution that we did before this, you would have the population mean and the population standard deviation. Well, now we're going to change this a little bit because we have a sample size that's 30 or above, or what we talked about with the normal distribution. So now, suppose X is a random variable with a distribution that may be known or may not be known. Using a subscript that matches the random variable, suppose the mean of X equals the mean of X, and the sigma of X is the standard deviation of X. If you draw random sample sizes of n, then as n increases, the random variable X will consist of sample means that tend to be normally distributed. And this is how we write it. We write it as large X bar approximates the normal distribution, and in this is our new mean of X, and this is our new standard deviation. This is different from our last standard deviation where we just had normal distribution. Remember, with normal distribution, we would have the mean and the standard deviation. Now that we're using the central limit theorem and we know sample sizes, we have to put the square root of the sample size below the standard deviation to get a new standard deviation that we're going to use. Okay. So again, the law of large numbers says that if you take samples of larger and larger size from any population, the mean of those samples tends to get closer and closer to the population mean. So think about it. If I keep sampling something over and over again of the same population, I'm going to get closer and closer to that true population mean. So from the central limit theorem, though, we know that as n gets larger and larger, the sample means are going to follow the normal distribution. The larger n gets, the smaller the standard deviation gets. This means that the sample mean, x bar, must get close to the population mean. So we can say that the mean is the value that the sample mean approaches as n gets larger. So the central limit theorem illustrates the law of large numbers. So those tend to get together and we look at them pretty similarly. So again, if I keep taking more and more samples, those sample means are going to start to get pretty close to that population mean. Okay. So the alternative one again, the central limit theorem for the sample means say that if you keep drawing larger and larger samples, such as rolling 1, 2, 5, or finally 10 dice, and calculating their means, the sample means form their own normal distribution. And some people might have seen this experiment where you give somebody a 6-sided dice and you tell them to roll it 10 times and then roll it 10 times again and roll it 10 times again. And for each of the 10 times you're rolling it, you take down what you got when you rolled it. And then from those 10, you average it together and you keep doing this over and over again until you get all these sample means and then you plot them. Okay. So again, remember we talked about this new type of mean and standard deviation over n that we are going to use because we're going to use the central limit theorem and we have a sample size this time. So again, to put it more formally, if you keep drawing these sample sizes, the distribution of the random variable, which consists of sample means, is going to be called the sampling distribution of the mean. The sampling distribution of the mean approaches the normal distribution as n increases. So in the random variable, x is going to have a different z-score associated with it than a random variable. Why? Okay, remember, our mean basically stayed the same, but what changed? What changed was the standard deviation over the square root of n, which we call the standard error of the mean. And if you look up here, that's what it did. It changed. So now our z-score is different. So if people ask for different, what is the z-score of this, and you have that sample, and you're talking about a distribution you don't know about, this is how you report that z-score. You solve it very similar to what we did with normal distribution. The only thing that changed is the square root of n underneath the sample error of the mean, as we call it, or the way that we look at that.